Right, so it's my pleasure to introduce Bosch Sensortec, Dr. Victor PANKRATIUS, who's the head of all their global software capability and engineering. And let's get going.
Thank you very much, and welcome everybody to the last session of the day. I hope we can provide you some interesting and entertaining information. First of all, I would like to show you some of the context that we are in. So where is sensing and tinyML and cloud and all these technologies in the bigger context? And what you've seen in the recent years is that things moved more and more towards the edge. So you have intelligence moving from the, say, cloud-centric systems getting into wearables. You see that going into mobile phones. You see that going into smart home, smart cars, smart industry, and so on. And what they all have in common that at the very edge, you need to get data from somewhere. You need to get information from the real world. And this is where sensors come in. And what happened to sensors in recent years is basically this. So what you see here is a concept outline of the smart sensors that Bosch Sensortec is producing. And you see that they're essentially more than just the sensing part. They're now a small computer, essentially, on a chip, which integrates things like an accelerometer with Micro-Electro-Mechanical Systems, a MEMS gyroscope, an application-specific integrated circuit, and a microcontroller. And what's so special about these is that everything taken together allows you to program sensors in a totally new way. So hardware and software in one package enable now algorithms on the sensors and, of course, tinyML. And yesterday we were actually joking that if you're really into tinyML and you've never seen or programmed of any of these sensors, you have never lived. So I want to show you what you can actually do and how amazing the applications are. So taking a step back, like, what does it mean for you as an application designer or an engineer, a student, a customer? What do you do with these sensors? So you have typically a system architecture where you have some kind of host processor, be it on your mobile devices, on your wearables, or other systems. And inside these sensors, you see more complex things like event-based sensor frameworks and memory, where you can place your own algorithms, or you can place some pre-configured algorithms that you can change or tune or train later in the field, for example. And why would you want to do that? Why would you want to put more intelligence on the sensor? And I think the key issue is that it's about energy. So if you're taking the bigger picture, you typically see in computer architecture courses people learning many things about the memory hierarchy. So if you have things in RAM versus cache versus registers, and how that differs in the kind of access times and so on. But you can put up a similar thing for energy. And the thing I'm showing you here is actually from a real product that shows you if you wanted to implement a step counter and you push more and more such logic down to the sensor, each time you're doing the next step, you're getting like 10x in energy efficiency. And this is really significant. Actually, this should be now part of any new textbook on computer architecture, which should also talk about the energy hierarchy in systems. So this is important for embedded systems, but I think it's also important looking at the cloud technologies that we have today, because if you are under the constraints of the tinyML, you are forced to be more efficient. You are forced to design algorithms that get along with all kinds of constraints in memory, in compute, and so on. And if we are able to develop algorithms and solutions that work well on the tinyML side, this can also have an impact back on the machine learning in a bigger picture. And you know how NASA is saying in order to get to Mars, we need to get to the moon first. So everybody's talking about moon to Mars. Well, potentially this could be our moon to Mars for machine learning in different ways. So let me show you some example applications, because there were many questions also in the discussions that I have. So what can you actually do in real life with all these tinyML applications and smart sensors? And there's a lot of solutions geared at different application scenarios. There's, for example, indoor navigation, where you want to navigate without GPS. If you're thinking about it, you're outside. If you're somewhere where signal reception works great, everything is fine, but the moment you are downtown with all skyscrapers around you, or you are in a shopping mall and you want to be guided to really pull that specific t-shirt that you're looking for, then all these nice solutions that work outside don't work well inside. And this is where inertial sensors can come in to bridge this particular gap. And machine learning and algorithms play a big role because you have to do all kinds of estimates, knowing from the last positions where you were to where you are now, and get rid of all the accumulated errors in your estimates. Sensors are also very interesting in sports applications. So for example, the pressure sensors are so precise now that you can put them, say, on weights, and if you're lifting a weight, or if you're climbing a ladder or going stairs up and down, you can actually see the pressure differences. Now that is fine from the measurement point of view, but of course you have also pressure differences due to other factors. You can be outside, you can have changing weather conditions, and this is where the problem becomes more complex, and you need more intelligence attached to the sensor in order to prevent false alarms or information that you might not want. If you're looking at where can you put this on your body, you can put things on, say, smartwatches, but also things in hearables, in wearables on the head, and do gesture recognition. So you can do gesture recognition based on your head or based on your gait, which has lots of interesting health applications. So you can use that for either characterizing your status, your health status, your well-being status, but also for prediction. Like you could see, for example, that you might have an issue not walking right, and you might get recommendations to do something about it. And of course, there's many more applications. This is just a small outline. One thing that I can dive a little bit more into is if you're looking at one particular solution, so say swimming, we have built something that allows you to put the swimming detection inside a smartwatch, inside the sensor, and then you can go and have somebody swim and do laps and characterize the speed, distance, or kind of technique you're using for swimming, all on such smart sensors. And if you're breaking it down architecturally, you see, well, there is an accelerometer and a gyroscope underneath, but there's a whole lot of other things that have to happen in order to make that work. So you need lap counts and stroke counts and swim styles, and each one of these boxes then breaks down to more machine learning techniques of different kinds. And I'll get to more details in a bit. So skimming at this level to yet other applications in sport analytics, we have systems in a chip packages like the BHI 260AP, and this is all like a 3 by 4 millimeter kind of package which integrates programmability and sensing all in one package. So what is so special about it that we can have machine learning all on the sensor. So by that I mean the training and the inference all in the field. So you don't need to be attached to a computer or attached to something that allows you to collect data and train and then create a model and push it back to your edge device. You can do this all on this sensor. And it's really interesting. Basically, the way it works is outlined here. You kind of learn the patterns from the time series of these sensors that are integrated. And then you use those patterns to personalize them to yourself or particular types of movements or movements of a machine or whatever you want to put this thing on, and extend it step by step with new activities. So the way it works is basically shown in a longer YouTube video that is linked in here that I encourage you to watch. But here's an example where you would count different types of repetitions in sports exercises. So you could say, oh, I want to do certain types of swings or certain types of jumping jacks and train this sensor to detect it for you. As a system architect, this is interesting because the sensor will then give you the semantic interrupts of the specific gesture or activity you've done. So you don't have to do that on your main processor consuming lots of energy. You can just wait for wake-ups and thus become more and more efficient. And there's more things you can do, so you can use this in different ways. You can either use this with pre-configured patterns and just ship this out to customers and say, well, this is something we have studied. We've done all kinds of user studies, and we pre-configure this with certain patterns. What you can then do is either use them as is or fine-tune them in the field. You can say, well, I'm doing the jumping jacks, but the way I do them is slightly different. So you can adjust this pattern detection to your particular personalized style. Then there's other applications where you can use this sensor to do all kinds of activity tracking. So add your own new activities in addition to the pre-configured ones. Or you can go all the way and say, you know, forget about this pre-configured stuff. I just want to retrain everything myself. And then you go and do something and say, okay, this is where it starts and this is where it ends. And you do this a few times, and this is how you can create a classifier, for example, for all kinds of applications. So in a similar way, I also want to switch now to different types of sensors, so from motion to gas sensing, and show you where AI is really making a difference in gas sensing. And here you see the same trend. Traditionally, the gas sensing as such, giving you raw signals and then having to process them on a bigger device, is now being smarter with more integration on the same chip. And this is also, you know, a few millimeters by a few millimeters. And you see inside the gas sensing element, an ASIC, and some programmable parts. And the thing is that if you were to look at the raw data, that wouldn't tell you much. So the raw data that comes out of the sensor is not really processable for humans. Because one thing that happens is it cycles through temperature ranges and then looks at certain patterns. And then it doesn't tell you much except that you as a human know if you hold this gas sensor into a particular gas or into a particular area where you have volatile organic compounds around. So for example, here you see in this plot, you see beer and cheese and chocolate. We've tried it out with wine and oil and other things, or peppermint and even sanitizer. And all you have to do is hold it into that area and say, this is sanitizer. And it learns the patterns, and the next time you hold it into that volume, it detects the sanitizer if it's there. This has interesting applications, for example, in home appliances. We've had a hackathon recently where somebody wrote a rotten avocado detector for your fridge. So it was pretty creative. People get very, very creative with this, and you can do too. The other interesting thing is that we can break away also from just looking at the sensor and looking at the fleet of sensors. So nobody says that we have to do tinyML just on the device. There's also an area where we can combine tinyML with traditional cloud-based approaches, and then I think there's really new opportunities out there. For example, you can learn from many different kinds of sensors what their particular biases or misclassification was. You can update them after the fact in your deployed devices. So imagine you have a customer buying a phone, and just by software upgrades, you can make this phone better after 1 or 2 years when it's out in the field. And that's really exciting because it's kind of upgradable hardware. And another thing is, to be successful in this area, you have to have a lot of domain knowledge. That's our experience. So it's not just about signals and signal processing and machine learning. You also have to know what you're doing, and you have to know what the customers or the users are expecting. Because the customers have their own area of knowledge, they have their own vocabulary, they have their own problems, and you really need to get quite deep into that in order to produce solutions that are really useful and accepted. So you need basically the intersection of 3 things. You need the data, you need the AI algorithms, and you need the domain context as well. And all of these require progress, so we should not neglect either one, but we need the intersection of all. And on the right side, you see where can you go with this? So starting out from the raw sensor data, where's the value chain of data? So as you add on top more functionality, you're actually adding more value because you are adding value by enabling motion detection in a much more energy efficient, much more ubiquitous way than it was before. Then on top you can go then and say, well, now I can do different kinds of pattern detections. So once you've done that, you can say, well, but now I can be context aware. I know where I am, and I can react with useful recommendations or useful predictions based on the situation of a user. And then from that, you can go to intent prediction. And as you go up and add more, this is where the value comes from, to actually produce a result that doesn't just tell the user that it's doing, or he or she is doing something that they already know, but they're getting something like a recommendation, you should do it differently. Or if you continue doing this, you're going to get a particular health issue. So that's the real value. And one thing I want to outline briefly to show you how much, in terms of details there is, if you are looking at table tennis. You know, you've probably all played table tennis at some point. But now imagine you want to detect certain strokes in table tennis, right? And you want to do it on the watch, and you want to do basically strokes on your left and on your right. So essentially, we have a professional table tennis player who tried this out, and I learned that you have things like a drive and a loop and a push and a block, and they all have very different ways of how you attack the ball, what's the speed of your racket, and what is the expected trajectory. And these are all nuanced details. But if you break it down to the sensor level, you see you have domain knowledge on the technical side, like technical domain knowledge. There you have knowledge like about the signal shape that you would expect from a racket swinging and hitting the ball. So then you know, well, I have to look at acceleration, I have to look at energy, because the energy can be very different. I can look at pressure, because there's pressure changes when you're hitting the ball. So with that, you can detect if you're just wiggling around with your racket or if you're actually hitting the ball at all. These are all details that play an important role when you really want to make it work. So from that, you're not even halfway through, because the only thing you've done is to kind of detect certain patterns for potential stroke intervals in your signals. You have to go much further than that. On top of that, you'd see the stroke sequences. And the stroke sequences would be, you know, you do a number of times, you're doing the right and the left drive or loops, for example, and each time it can be slightly different. So this is where you need AI, because you could build a matched filter, but human motion is also very personal and very different depending on the situation. So it makes a lot of sense to think about machine learning in this case. Now, when you're done with that, then you come to talk to the experts and the professional players and say, yeah, but I actually want to know all these particular other classes, and then I also want to know something about the gameplay. So you need some kind of a state model that knows what you've done before, because certain times you cannot do certain sequences, right? It could be humanly impossible to turn yourself in certain ways. And this is domain knowledge that you can use to self-correct the predictions of the AI. So with this, you can introduce self-corrective capabilities and take care of some of the false positives or false negatives in this process. But it requires you to dive into what makes table tennis and what makes a gameplay in table tennis. So all of this is in an unoptimized versions. You can get it down to 94 kilobytes. If you're spending more time, you can push it much lower. But this is just to give you an idea of how many things there are you have to think about in order to get something that is acceptable in a real scenario. And now for the last part, you might have the question, so how can I get my hands on this? How can I try it out easily? And we've partnered with Arduino to put most of our flagship sensors on this teeny tiny Arduino board. So this board is stamp-sized. You can get it online, and what you'll find on this board is the BHI-260 AP that I just described. You will see the BME 68080, which is the gas sensor, which is programmable. It also has a pressure, temperature, and humidity capability. There's a pressure sensor and a magnetic sensor. The interesting thing about this is this board has Bluetooth and a charge controller on it, so you can attach a teeny tiny battery on it, so same size as the board. You can build a whole sensor network out of these boards and place them anywhere. And it also works with TensorFlow and other tool chains, so feel free to try it out, specifically TensorFlow Lite, for example, and put it on your wrist or on an object and try to do some machine learning with it. So finally, we will see this community growing, and we already see it, and it's really thriving. There's a lot of interest. There's a lot of cool stuff going on the hardware side, but also on the software side. For example, if you were asking yourself, okay, how do I build other tool chains on top? What if I need graphical user interfaces for my data collection and so on? There's even open source projects like edgeml.org that are around. They are under MIT license. It's all open source, and you can either reuse their code or do a version of it or contribute. So there's many ways to do it. And with this, I hope you are inspired. And if you want to try it out, let us know. We're really curious to see your own use cases. So thank you very much.
Hello. Yeah, thanks for the talk. It's not really a question. It's, I guess, more on your thoughts. So, I mean, compared to, I guess, the image community, the challenge in the sensor community is level data is very hard to get by in this community because it's super hard to interpret. See for example, the IMU trace and kind of interpret what's going on. So I was wondering, what are your thoughts on learning from, I guess, unlabeled data? And I guess this is more important when you push a model to your clients, and you might have a fine-tuned model, but then suddenly after a few days, the pattern of those activities might change. So there you might need some way to detect those changes. So I was wondering, what are your thoughts on learning from unlabeled data on the device or on the edge?
Mm-hmm. Mm-hmm. So I think this is a really interesting application area. So thanks for the question. That's an excellent question. There's a lot of work also going into personalization. So trying to pre-train certain things and then use pre-trained models to fine-tune and adapt them when it's at the customer. I think this has the potential to bridge this last mile, because usually when you're trying to personalize something, it can be very hard to get good results for every specific person, no matter what you do. So our approach is also to enable customers to either use some pre-configured models, but then allow to have each customer say, well, this particular pattern doesn't fit for me, so I want to either adapt it or I want to replace it. And I think that this is one of the key questions, but clearly there's more work to be done. We're not anywhere near where we could be, and this is also where all of you in this community have something to do. So I hope we can do it together, because there's some really exciting applications. And of course also the PhD students and everybody looking for a thesis, please go ahead. This is a really fruitful area to be in.
Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymex, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.